Hello class, so in this video we're going to be talking about estimating the area under a curve. So let's say that we have a function like this, so this is f(x) equals x squared, and we're trying to find this gray area right here, the area under the curve from 1 to 3. So first of all, let's talk a little bit about why we even want to do this in the first place. Because you're just finding an area under a curve, so like why? The thing is, it tells us something called accumulation. So easiest way to kind of see this as a physical example is if we look at this as the velocity of a car or something like that. Then we find the area under it. Essentially what's going to end up happening is you're going to be multiplying somehow this way, and you're going to get, let's just say, seconds times meters per second. Something like that, right? Then the seconds will divide out, and then you just have meters left. So that gives you the distance. In other words, if we think about it physically, if we're looking at a velocity curve, it tells us how fast the distance or displacement is changing. And therefore, if we find the area under it, it tells us how much distance was accumulated from that change. So that's the reason why we look at area under a curve. It actually tells us quite a bit about some sort of a system. So how are we going to find it then? Well, one thing that would make things easy is to actually just look at, let's say, a rectangle like this and a rectangle like this. Find that area, we can estimate it. So here we're just estimating, we're not going to get the exact area just yet. So we can use areas that we know, like rectangles, because the area of a rectangle is just base times height, right? So we can just do that. So let's look at this for example and just do stuff with it. So here we have f of x equals x squared, and if we look at what's going on here, we see that there is a certain distance in between each of those. So that's going to be our base. And then if we look going up and down like this is going to be our height. So what are some things we notice about this? For the bases, that's a bit easier to see first of all. So for the base, they are all equal to 1/2 or 0.5. Well, why does this make sense? Well, if we look at this interval, we go from 1 to 3, and we're dividing it into 4 pieces here, right? So we can think, well, we want to get that entire distance and divide it by 4. Why are we doing it by 4? That's just an example, so you're not always going to necessarily use 4. Well, we get 2 over 4, then 1/2 or 0.5. Okay, so how about the heights? Well, what we notice is the heights and the function actually intersect. So here, as we look at each of these subintervals, what I'm doing is actually choosing heights based on the left-hand side of each interval. So what we're actually doing here has a special name. It is called a left-hand sum. You can also call it a left-hand Riemann sum. So this is the name of a mathematician. He, long story short, created this. So Riemann sums. So for the height, what we can do is get the x values of each of these points over here, and then the x values can give us the y values, right? So let's look at what they are. So x values for heights. We see we have 1 right there, and if we go 0.5 over, then 1.5, then 2, then 2.5. That's pretty simple, right? Well, let's find another pattern there, though. So we know that we went over by 0.5, right? And then over by 0.5, then over by 0.5. Well, what is 0.5? That actually is the base. So there's actually a special term we have for this in mathematics, which is delta x. So delta just means change in, x is just a variable. So notice that each of these bases is just a change in the x-axis. So you can just add delta x over and over and over, and that'll give you each subsequent point. The x values, that is. So let's look at it this way. Start with 1, and a 1 plus 1 delta x, and a 1 plus 2 delta x, and a 1 plus 3 delta x. Okay, so what do we notice? We are just adding delta x's, right? How many are we adding here? Well, none. So 0 times delta x. That might seem a little redundant right now, but you'll see why it's useful later on. So we see then that the area itself is going to be the summation of a few things. Area is going to be base times height, right? So what's the base? The base is the same the entire time. The base is always that delta x. And then the first height is going to be f of this. F of the first x coordinate. So 1 plus 0 delta x. Alright, and then we add the next base, which is still delta x. Then the next height, which is f at the next point. 1 plus 1 delta x. And this just continues on and on and on until we get to the last part. So here are the next things that we get. Alright, so if we just do that all out, then delta x is 1/2, right? So I'm just going to factor that thing out to the front, actually. And then we have f of 1 plus f of... I'm going to do this as fractions. Instead of 1.5, I'm going to do 3 over 2. Plus f of 2 plus f of... that'll be 5 over 2. Just because we're squaring things, and it's easier to square a fraction instead of a decimal. Alright, so f of 1 is 1, f of 3 over 2, that's 3 over 2 squared, so 9 over 4, plus 2 squared is 4, plus 5 over 2 squared is 25 over 4. So 1 is the same as 4 over 4, 4 is the same as 16 over 4, so just going to add those together. So let's see, 4 plus 16 is 20. 20 plus 9 plus 25, all over 4. So we end up here with, let's see, that's 45 plus 9 is 54. All divided by 8. So let's see if this can divide somehow, right? So we know at least 54 is even, so let's divide these by 2 each, then we get 27 over 4, and yes, that's the most that it'll reduce. Alright, so let's try the next one then. Over here. So, what do we notice that is different? We notice that it's the same area that we're approximating, but we have different rectangles. What's happening instead is we have this interval, we're dividing it into 4, but instead of using the left hand points, we are now using the right hand points, as you can see right here. So right side of the interval, right side of the interval, right side of the interval, and surprise, surprise, right side of the interval. Okay, so the base is still delta x equals 1/2. So that's the same thing. How about the heights though? So now we have new x values. So we're still starting from 1. However, in this case, that's not starting at 1. the x values are going to start at 1.5, and then 2, then 2.5, then 3. In other words, we start with 1 plus 1 delta x. Then we get 1 plus 2 delta x. And then 1 plus 3 delta x. And then 1 plus 4 delta x. Okay, so then that means the area is slightly different. So the area is going to be, I'm just going to factor out the delta x because we have it in common in all of them, as we saw up here. In common, so you can just factor it out. Alright, so we get f of 1 plus, I'm just going to write this again so that we can see a pattern that's going to go on. So if you're watching, you don't necessarily need to write that all completely out like I am, but just pay attention and look at the pattern that's going on. Alright, then we end up with 1/2 times f of, now we're going to start at 3 over 2, then 2, then 5 over 2, and then 3. Then simplifying that, we get, that'll be 9 over 4 plus, I'm just going to do these all over 4 immediately, so that's just going to be 9 over 4 plus 2 over, let's see, that's 4, so 16 over 4, and then that's 25 over 4, and that'll be 9, so that's 36 over 4. And that was all divided by 4. Okay, so adding these things together, let's see what we get. Let's see, the 6's and the 9 can combine to make a 10, so 25 plus 36, that'll be 61 plus 9 is 70. 70 plus 16 is 86, all divided by 8. So 86 is at least divisible by 2, so let's do that. So that'll be, divide that by 2 each, then we get 43 over 4, and that's all that can reduce. Okay, so let's look at what we got in sigma notation, actually. So for the left sum, we got L sub 4. So L sub 4 just means you're using left-hand sums and 4 rectangles. And then R sub 4 is going to mean right-hand sum 4 subintervals. So on the left, what we got was, we had delta x multiplied in everything, right? So we can already say summation of delta x times f of stuff. Well, what is the stuff? Let's look at that. So we have 1s in common in all of them, and then what changes? We have 0, 1, 2, 3. That changes. Delta x is still the same. So we have 1, and then we have delta x there, and we're adding something times delta x. I'm going to make my index k. So if we start at 0 up here in the summation, then that means we're going to have to somehow make the first number here 0, and then the last one 3. So then this could just be k, and then we can just start that at 0 and then 3 and make that easy. And then I'm going to actually use a very similar thing in order to do the right-hand sum. So let's look at that here. Again, we see that we have delta x, so let's just write that out in front. And then we have some f stuff. So we have f of 1 plus something times delta x. So here we go from 1 to 4. So we can just easily make this k equals 1, go to 4, and then just make this thing k. So this is a very simple way to look at that. So what if we didn't just have 4, but we had a lot of different rectangles? So for one thing, delta x, let's talk about that real fast. So let's say we're finding area of f of x on some interval from a to b with n rectangles. Well, delta x, that would change a little bit, right? So the logic we had was, let's take the distance between that and just divide it by how many rectangles we have. How many do we have? N. So delta x is going to change to just be that. And we can generalize these as being... So 1 was where we started over here, right? X equals 1. So that's our first part of the interval, because this was area from 1 to 3. 1 to 3. So this could just be A instead of 1, because that'll just be the generalized case. Same thing down here. And so how many rectangles did we have here? We had 4. So how does that relate to these other numbers? Well, that would just be n, because we're saying n number of rectangles. And here, that wouldn't be 3 necessarily. That'll just be n minus 1, because we had 4, now we had 3 over there. Since we have 4 up here, which is how many we have, we're going to get that. So this is what you will get in the general case. So, because I don't want the video to go on way too long, I'm going to do the next example with this just really quickly. So here we have f of x equals x squared. We're going from 1 to 3. 8 rectangles. And this is going to be a left-hand sum. So L sub 8. Alright, so actually, let's figure out delta x first. 3 minus 1 divided by how many rectangles? 8. So we got 2 over, not 4, 2 over 8. So 1/4. Alright, L sub 8, that would just be then summation k equals 0 to 7 of, I'm just going to write delta x and then f of a plus k delta x first. That'll just make it a little bit easier to do and to remember that. So this equals summation k equals 0 to 7 of 1/4 times. So this is going to be f of 1 plus k times 1 over 4. So I'm just going to write that as k over 4. So I'm going to factor out the 1/4 first because it has no k, so the summation doesn't affect that at all. K equals 0 to 7 of. So 1 plus k over 4 is the input for the function. The function is f of x equals x squared. So we're going to get this thing squared. So don't forget that 1/4 if you do factor it out. Of, okay, first thing squared plus 2 times that product. So 2 times k over 4 times 1. So k over 2 plus the second thing squared. Not 4 squared. I mean 4 squared, not just 4. Alright, so if we have this then, we basically have a formula that we can work with. So there are special sums you can use to get the exact values of these rather than just directly adding and multiplying and all that stuff. So I'm just going to leave this here for now because this has gone on long enough. So this is where you should probably get to if you're just starting out with sigma notation and finding an estimating area under a curve. There are more things you can do. You'll be able to check out another video later on that talks about this then. Alright, so hopefully this was helpful, and see you all in the next video.